Okay, so today we are going to introduce a property of the optimum for two things. Today we first talk about the property. There's a theorem. Properties of the optimal solution. And then we talk about how to find that solution. Okay. So first things first. So it turned out that here it turned out that when we talk about the properties of the optimal solution, it's easier to talk in the polynomial domain than in the frequency domain. Okay, so here, let me rewrite this expression. Okay, because this expression involves omega, frequency responses, and weighting functions. But it turns out that there's a one-to-one mapping between omega. Our omega goes from, should I say, from 0 to pi, right? Our omega is defined in the region 0 to pi. But if we use that change of variable. By changing the variable, by change of the variable from omega to x, our task becomes to find, at least conceptually, to find an optimal polynomial. Let me say that again. So by defining this transformation from omega, change the variable from omega to x, we are going to find an optimal polynomial. Okay, and that polynomial is going to have some nice properties. Okay, so why can I say that? Because now, A of omega is simply, if you will, we say this is A, let me use this, A filter of x, right? Because A of omega is something, a polynomial of cosine omega, right? And cosine omega, now we have changed the variable, and denote this by, we are going to call it x, okay? So now, this A of omega is a polynomial of x. So this is a polynomial of x, where x is simply cosine omega. And note that the desired response now in the omega, if omega is the variable, then it's a low-pass desired response, right? But now when we define x equals to cosine omega, we have the kind of desired response becomes, in terms of x, let's take a look, okay? X equals to cosine omega, so omega equals to 0. DC corresponds to x equals to 1, right? Because cosine 0 is 1. Cosine 0 is 1. So if now the horizontal axis is x, then we know 1 represents DC. 1 is DC. And minus 1 is pi, the highest frequency. So now we're kind of reversing the direction. Lowest frequency to the right, highest frequency to the left. Flipping it over. This change the value of x, and we define the change of value of x as cosine omega. Okay? So now 1 is DC, and minus 1 is pi with the omega, kind of omega axis. So the direction has been reversed. Okay? So now our desired, the target of our design, we want to approximate this as much as possible, right? We want to find an optimal design which approximates this as much as possible. Now, so we have a low-pass design, therefore we can define some kind of edge x, the corner x value for the passband and the starting x value for the stopband. We say that we want to find the edge x value, x the period, the edge of x, the edge of passband in terms of x, and the edge of stopband in terms of x. Okay, so now in between we have the don't care region. In between we have the don't care region, which has a zero tendency. Okay, so now revising everything here using the change of variable. We are kind of just revising our solution as to still we are trying to find an argument which minimizes maximum error. And we are still going to search in L+1 dimensional space. And now we are minimizing the maximum error among x from -1 to 1. Okay, the maximum error and the weight function can also be after the change of variable, the weight function is also defined on the x domain. Now it's defined on the x domain, and what else? And then the absolute error, A of omega is now denoted as A pupa of x minus h desired, the desired response in the x domain. Still, everything remains the same, only changing omega to x. Okay? Only changing omega to x. That is to say, if you have a design, okay, if you have some kind of design, not necessarily optimal, whenever you have some kind of design, a frequency response, and we are going to look at its maximum error from 0 to pi, within the frequency range 0 to pi. That's equivalent to finding the maximum error. That maximum error is not going to remain the same when we change the variable from omega to x. And that is long story short. Okay? So this is just to emphasize that the same, if you have any kind of a design, okay, and that gives you a frequency response, and the maximum error amount in the frequency range is equal to the same maximum error. It doesn't change after changing after we perform the change of variable. Whatever the larger error is that much, it remains the same as much after the change of variable. 我把它画清楚一点。So like to say, suppose that for example, suppose that we design a filter and it has this frequency response. Kind of ugly. I know it shouldn't go like that. It is like so ugly. Okay? That's an ugly filter. And what is the maximum? Okay, we suppose that we apply some penalty. So you can say, okay, maybe right here it has the largest, the maximum absolute error. That is so much. Right? That's the maximum absolute error. This is the maximum absolute error. Maximum absolute error. Maximum weighted absolute error. You know? So of course, by weighting, we need to apply the weighting, but you know what I mean. So the maximum error is so much. But the change of variable from omega to x is only kind of stretching in this horizontal dimension, right? And we flip, when I change a variable, this ugly response is going to look like that, and going up, and like that. Right? And that's still the same maximum error, same maximum absolute error. It doesn't change after a change of variable. Because our change of variable is only like stretching in the x from x omega to x to the horizontal domain. The height of the error will not change. Therefore, the optimal solution that minimizes this in the omega domain can be the same optimal filter that minimizes error in the x domain. Because x is merely the change of variable. 大家了解吗？can we continue? Can we continue? Okay, so to summarize, once we have a design, however we design our filter, okay, this is a design. This is a design. When we have a design, then we can calculate this polynomial. Any design corresponds to a polynomial. Okay? And so our job is to find the vice versa. Any polynomial here, for any given polynomial here, we can back calculate the design. There's a one-to-one mapping from the design of our sample values to the what polynomial is. Okay? One-to-one correspondence between the set of all possible polynomials. The set of all possible polynomials, fourth order polynomial, defined on -1 to 1. That's a fancy thing to talk about set. This is a linear space, a vector space. Okay? There's the one-to-one correspondence between the vector space R, what I mentioned, to the vector space of all the polynomials, all the real value, real coefficient polynomials defined over the closed set and closed interval -1 to 1. One-to-one correspondence. Okay, yeah. Okay. So this makes our life a bit easier. So eventually, we are going to simplify our task by asking that we are going to find the best polynomial. The task becomes to find the best polynomial, an optimal polynomial that approximates the desired function. It is the argument that minimizes the maximum error maximum weighted absolute error. This is now our new task. We want to find the argument that minimizes the argument, all possible polynomials that belong to the set of L plus 1 order polynomials defined over the closed region, closed interval, -1 to 1. Such that this polynomial, this unique polynomial, would minimize the maximum weighted absolute error. And where we know that this is just simply given, low pass and the ideal response. Okay? This is simply given, this is simply assigned by us. We can choose to control the penalty. Okay? This is assigned by us, this is simply given. And now our task is to find the polynomial. Once we find the polynomial, we can back calculate the filter. That's the idea. Okay? So now okay to everybody. Once we find the optimal polynomial, then we can it's rather straightforward to back calculate, to calculate the corresponding filter. Okay? So now we are ready to introduce this theorem. Let me first give you a highlight of the theorem. Okay? So now, our desired result is a discontinuous function defined over from -1 to 1. Okay. This goes with -1. So this is our let's say this is our desired result after the change of parameter. This is a low pass filter, okay? A low pass ideal response. And now let's kind of go back to high school mathematics. We high school mathematics. So we are trying to imagine now let's take an example. Okay? Take an example of L equals to, let's say L equals to 5. L equals to 5. So P5 so we are going to think about all possible fifth order polynomial of fifth order or less. Okay, 5次以下的都像是 okay. We're also think about the space of all possible polynomials of order 5 or less. And you can plot for any given polynomial, you can plot it as a function of x. And we know that fifth order polynomial at most has how many turning points? You know that, right? A second order polynomial is a parabola. Third order polynomial may look like this. Fourth order may have like that. And fifth order at most can go up and down like that. So that's L equals to 2, 3, 4, or 5. Now I want you to think of the set of all possible fifth order polynomials to see how they can best match this ideal function. Ideal low pass low frequency on the right, high frequency on the left. So if you just kind of think of graphically, maybe I can try drawing a polynomial. And I'm allowed to have at most so many turning points before it, right? Okay, so let me give it a shot. So maybe my filter can look like this to green. Maybe my filter can look like, I'm just trying to be lucky, okay, to see if I'm getting lucky. So you know what I'm trying to see? I'm trying to draw a fifth order polynomial that really resembles this nonsense. We should cheer me up. I have 45 seconds to do this. Oh. I'm afraid I'm running out of the turning point. I don't know. Something like that. How many do I have? Oh, 1, 2, 3, 4. I'm lucky. This looks like not bad, not a bad job, right? So this is exactly the task we are having now. We want to find a polynomial given L. L might be not 5, 6, or even higher. Okay? But we want to search in the L plus 1 dimensional space of all the possible polynomials under degree L. Find a polynomial that sort of fits the ideal function. And of course, any polynomial is going to be a continuous function. It's going to have turning point, it's going to be smooth. So we are again trying to approximate a piecewise linear function with a smooth polynomial. There's always going to be error, right? At every frequency. Now we want to find any one of them that minimizes the maximum deviation. So think that I have a maximum error right here, which is kind of large. Okay? This is my maximum error now. That's my maximum error. Right here. And we are kind of doing a good job because I control my error to kind of within so much. The positive, the negative, now this polynomial I'm drawing here, we evaluate how good the approximation is by the cost function. Okay? We are evaluating the goodness of our fitting by a cost function. And in this case, the cost function is like a maximum error in all x. In actually maximum weighted error. So this is interesting. This is, of course, in the middle we have to connect dots from here to here, but in the middle we don't care. This is a don't care region. Right? Any comments so far? So the job becomes to find a polynomial fit to a piecewise linear function. Can we go on? So that's our job. So now there's a theorem that I want to share with you. It turns out that before I switch to my PowerPoint, it turns out that in this kind of optimal optimization problem, the best fit, the polynomial that best fits, that fits the best to our piecewise linear function, that polynomial has an equal ripple property. Equal ripple property. That means that this is an alternating. The alternating theorem. It turns out that any such best fit would have have to have at least L plus 1 alternating points. The optimal filter, the optimal polynomial would need to have actually L plus 2 or L plus 3 alternating points.
Yes.
And what is an alternating point? That means the optimal solution would have L plus 2 or L plus 3 different points. And if you look at those, the error at the alternating points, the error changes sign. So for one alternating point, the error is plus maximum error. And for the next one, it's negative maximum error. And for the third one, it becomes plus maximum error. And the fourth one would be negative maximum error. Okay, so that is to, if I draw it in the picture, and now we are trying to fit this ideal function, right? Ideal function. It turns out that the best solution would have the best solution will need to have equal, so that's why I call equal ripple property. Equal ripple property. The ripple, the height of the ripple is going to equal at multiple places, that is to say. And more rigorously is referred to as the alternating theorem. Okay, so here I'm going to show you in a PowerPoint slide that we will need, the optimal solution has this property. It's a necessary and sufficient condition for optimality. Okay, so this optimal approximation will have 1, 2, 3, 4, 5, 6, 7. In this case, 7 different alternating points. So the first point has the maximum absolute error. The second place also has a maximum absolute approximation error, but now the sign changes. It goes under. And the third one goes above. The fourth one goes under. The fifth one goes above. The sixth one goes under. Is that clear? So that's kind of a theory, a property. We know that however we're going to find it is another business. But we know that there is a theory that tells us that the best solution will need to have L plus 2, in this case L plus 2, or L plus 3 alternating point, where the approximation error reaches maximum and the sign alternates. Any question here? So this might sound totally new to us, but just, I want you to keep in mind that eventually this is just find the best polynomial fit. The problem, we have now finally formulated our filter design problem as a polynomial fitting problem. And that's the spirit. Okay? Once we get the best optimal polynomial, then we can backtrack and calculate the best filter in terms of the sample values, which is also to given the Chebyshev polynomial. Okay? So let me switch to my PowerPoint. Okay, finally. I just want to show you briefly. So next time we continue talking about then how do we find the optimal filter. Okay? How to find it is quite tricky. So we can cross over next time. But today, let's see a few examples. So it's called the alternation theorem. Okay, so go ahead and move on to those. The alternation theorem and the corresponding algorithm, the Parks-McClelland algorithm for optimal filter design. Parks-McClelland, or PM, the PM algorithm is an algorithm that helps us to actually find the optimal filter. But the other filter will have the property that's guaranteed by the theorem, the alternation theorem. So here is again our problem formulation. We have a desired response. We want to try to approximate. And pass band, stop band, okay? Same notation. And next, so this is a typical frequency, some kind of design. Okay? Now we want to imagine actually every this design is has a corresponding polynomial after the change of variable from omega to x equals to cosine omega. Okay? So of course we can define an error. The error would be the pass band, stop band. And here is the theorem. Okay, if we have a polynomial, we're searching in the space of all possible nth order polynomials. I want to find, so the notation is a bit different, but it's basically the same thing. We want to find a polynomial. Find a polynomial x that minimizes the maximum weighted absolute error. Okay, same problem formation, and here is the theorem. A necessary and sufficient condition for the unique optimal solution will have to possess this property that there exists at least L plus 2, actually at most L plus 3. Okay? At least L plus 2 distinct values of x. In the region Ft basically is minus 1 to 1 in our case, such that the weighted absolute, or the weighted error, okay, actually here the error is defined before taking absolute value. Okay? The weighted error here, the sign of the weighted error changes from, you go from one point to the next. Okay, so at one point which is the plus maximum error, and the next point will be exactly minus maximum error. So these are called the alternating points. And this theory is referred to as the alternation theory. Okay, when we go from one point to the next, actually in the order of decreasing or ascending with the descending order. Okay? The sign of the approximation error needs to change, and otherwise it's either plus or minus maximum absolute error. From point 1 to point 2 plus, from I equals to 1 to L plus 1, there is a total of at least L plus 2 of such points. So what would be an example? And I just flash this. There is if you are interested, you can find the paper. This is a paper written by a famous professor, a prestigious professor at Caltech, California Institute of Technology. A very famous person in signal processing, like Newton. Okay, and he has a simple proof. So here are a few examples. So let's check whether or not these functions, these are all examples. They might or might not be optimal, but here we are seeing 3 polynomials basically. But in this case, they must be designed in high pass filter with minus 1 to 10 and minus 1 to 1. Okay, high pass design, and here for this polynomial, it works pretty well. It has 1, 2, 3, 4, 5 alternating points, but only 5, not enough. This is a 5th order polynomial. Okay, 5th order polynomial having only 5 alternating points, so then according to the theorem, it's not enough. Because the optimal solution, the necessary and sufficient condition would be to have at least 7 such alternating points. The second example, 1, 2, 3, almost there, but no. And now this point cannot be counted as an alternating point. So 1, 2, 3, 4, 5, only 5. Again, it's not optimal yet. And the optimal solution is here. 1, 2, 3, 4, 5, 6, 7, 8. 8. 8 is more than L plus 2, which is 7. So this is optimal according to the theorem. And we're not going to through the proof of theorem, but these are showing you how to count the alternating point. We'll count what is it. Okay, any questions here? Anyway, so we continue this session next week, right? So I'm going to switch my time to the TA to give you back the